Happy birthday, buddy. When John and his comrades here invited me to give a talk, I said, well, the only possible excuse is that my name is on a paper that seems to be well read lately. But otherwise, I left academia 35 years ago, and I have not looked back since. No, I'm kidding. But I've been active in private industry, including 25 years of my own business. And I'm retired from that. And now I'm free to talk about anything. John said, take a walk on the beach, talk about anything you like. So I'm going to do exactly that. I took him up on it. I'm going to walk on the beach, but this is going to be a very big beach. The sort of boundary between math and physics. So I'm going to cover a lot of ground on topics I don't know anything about, and maybe unfamiliar to you as well. So let's see what happens. I've just started my clock. Okay, so let's go. Something from nothing. First, I want to say that, especially for the young people who think that good problems are running out, there's nothing like that. The universe is vast, and so is unattained knowledge. There's no shortage of problems to work on, and in fact, they'll just continue to multiply. So don't believe any of that. Now, math and physics, we all know, of course, distinct topics. I mean, we know where the boundary is. Physics talks about things like figuring out the motion of the planets. Math worries about things like classifying manifolds up to some equivalence class. So these are totally different things, and we all know that they're very different. I'm here to tell you that's a lie. Okay? So now there are a lot of opinions between engineers who think math is a human-developed tool and physicists who think that math is actually discovered and is closely linked to physics. Just pay attention to what develops over here. Looking at some facts, well about Newton calculus, which planetary motion, but in fact is used everywhere. Fourier, I don't even need to tell you. Quantum mechanics, but it's used in electronics every day. Einstein's relativity is used in GPS every day, and you wouldn't get to work without Einstein's relativity on time or even in the right place. But since then, a whole dam has collapsed in terms of the interaction between math and physics, and I'll tell you a little bit about as what I know. Okay, let's talk about it then. The one takeaway from this section I want you to learn is the universe is not actually made out of anything. It's all math all the way down. You think the universe is made out of atoms. Atoms are made out of particles, but those particles are just fields. There's no substance to it. And that's why, that accounts for 3 of the 4 forces we know. And gravity, well, there's pure geometry. There's no substance to the thing. And that's why math and physics are fundamentally connected, and there's no other way. Okay, now let's talk about the math and physics. So let's talk about the math a little bit. Of course, Newton very well. But the takeaway I want you to walk away with, to optimize something so that the first root is 0, that's, of course, very well known. You teach it in calculus classes. But here's something you might not know too well, that using Newton's laws, you can compute the escape velocity from a massive object. And then if we set the escape velocity to the speed of light, you get a number for what the radius means, that if you can cram mass m into a radius that size, then even light can't escape it. And it's interesting that 100 years after Newton, people did actually think about dark stars, although they didn't know about, think about they would really exist out there. In fact, Einstein even didn't believe that black holes could exist. And I may get to that. Now, the modern version of df dx equals 0 is really del S equals 0, where we have some function that nature wants to minimize or optimize in some way. So you know all about this. But what that tells you is that well-known laws like Maxwell's equations can be turned into much more compact notation and tensor notation. You know that already. We tell you about special relativity. You're all probably familiar with special relativity, but that you know that it leads to time dilation, length contraction, and things like that. The one takeaway that you may not be as familiar with is that there's no such thing as simultaneity. 2 things that you think happen at the same time are really only your perception. Everybody else's perception, even for other observers moving without acceleration, so-called initial reference frames, may see one happen before the other in both directions. which means that now what you consider now the present may be somebody else's past or their future. Past, present, and future are all on the same footing. Now, you think that's, of course, some physicist's, dream or nightmare, but in fact, that sticks. Even to this day, nobody knows an answer to that, okay? And if you think quantum mechanics can overturn it, you're wrong. Quantum mechanics cannot overturn this reality. So we live in a world that's much, much stranger than we all know. But now you know some of this stuff. I hope to tell you some things that you might not know that might shock you. Okay. General relativity. I won't teach you anything, by the way. I'm here just to pretend to remind you of some topics, and you can pretend to be reminded. Okay. General relativity you know well, or hopefully you know well, but the interesting thing is that, and Einstein proved things that you couldn't get from Newton's equations, but interesting is that Carl Schwarzschild published in the same year, or at least developed, a solution, an exact solution to Einstein's equations, namely the Schwarzschild solution. And it's to this day, it's the most important solution found of Einstein's equations. And in it, there is that Schwarzschild radius, which is exactly the number we gotten from Newton's equations. So that's unusual. Now, I won't teach you, calculus of tensors, but the interesting thing is that in flat space, geodesics are straight lines, so they have a very simple equation. But in curved space, there may not be any straight lines, that objects move on what are called geodesics, and the equation for geodesic is a little more complicated. It's got a second term, which involves something that deeply connected to the underlying metric. Okay, so the one takeaway I want you to walk away with in general relativity is that matter tells space how to curve, and curved space-time tells matter how to move according to the geodesic equation. Okay, so far so good. I think you may know all of this stuff. I don't think I've taught you anything you don't know. Quantum mechanics you also know pretty well, but the one takeaway I want you to have is that actually Schrödinger's equation, when integrated, it really shows you that the evolution of systems is completely unitary and deterministic. So you think quantum mechanics has a lot of indeterminism, but Schrödinger's equation is really fully deterministic. In fact, it can go backwards or forwards. It doesn't even care. That's bizarre. Okay. But the indeterminism comes from observing something. When you want to interact with something, then there's a collapse of the wave function according to the Copenhagen interpretation. If you don't like Copenhagen's interpretation, go with the many worlds, where at every interaction, the universe splits into a potentially infinity of universes where every possible thing with non-zero probability happens. You like that one better? I don't know. You're stuck with either one or the other. That's really where we are. Okay. Heisenberg uncertainty principle, this crowd knows this well, but what you may not be as familiar with is that this inequality breeds fire. In reality, because we have quantum fields everywhere, there can be no such thing as a vacuum, and out of nothing, you can borrow energy for a very short period of time, create particles, they disappear. It's truly bizarre that this inequality holds everywhere in the universe, and it means that there's no such thing as a vacuum. Okay. HRT, I don't need to tell this crowd. You know all about it. Okay, and I'm very happy to have my name on that paper. It was a great paper, and we had no idea at the time that this was going to have that much of a lifetime. Crisis of the continuum, you don't know what that means yet, but you know about the continuum, the real line. Everything we do in mathematics is based on this real line. We move along smoothly. We expect all of space to be translation invariant. We expect time to be time translation invariant. We expect rotational symmetry. And according to Noether's theorems, those lead to conservation laws, which are used everywhere in science. Now, in reality, though, in physics, those kinds of symmetries can only exist in flat space. You live in curved space, there is no such thing as space translation symmetry, time translation. So you might not even be able to define time. You may have space times where time is not well defined. What do you do with that? Now you're really in trouble. So then that begs the question, is the real line even a good model for our universe? And I'll say more about that and you'll be shocked. Okay. Physics has really some really dirty tricks we know all about that. I'm going to expose them. Let's talk about some of their dirty laundry. They do, without justification, take time to be imaginary. Whoa. That destroys, for example, special relativity as it is right there. Renormalization is a funny name for canceling one infinity with another and getting a finite number. And then they say, oh, this is the right answer. Baloney. None of us can believe something like that. And this really takes the cake. Dimensional regularization. When they found Yang-Mills fields and they used to model them for everything from electrodynamics to fermions like protons and neutrons, they found that the integrals always diverge. What they did was something truly amazing. We heard about a real line, a real number dimension in a couple talks earlier. Well, these guys go off the deep end. They set the dimension to be a complex variable. You don't like d equal to 4? Analytically continue the dimension. Who would have thought of that? And then they take the limit off the real line to 4, and they get a finite answer, and behold, it agrees with experiment. Now, how the hell do you get that? That's complete baloney, okay? And yet, they found something that works. That means that they understood something we don't understand about our own reality. That's bizarre. Okay. Now, mathematically speaking, I'm going to put the mathematician hat on for the moment. All this stuff is garbage. Quantum mechanics, the path integral approach uses integrals over a vast space of paths. But unlike the brachistochrome problem, where you start somewhere, you end somewhere, and we know there's a minimizing curve, there's no such thing here in quantum mechanics, because when you start somewhere, it can still end up anywhere you want, does it? There's no one place it goes to. It has an infinity of possible next positions or next quantum states, and those things are parameterized by paths all over the place. So this integral really doesn't exist. And on top, you're integrating something oscillatory. How the heck do you do that? That doesn't make any sense. So they come up with some good dirty tricks, and I'll show you. Okay, quantum field theory, now the problem gets even worse, because now you have to consider all possible configurations of fields over 4-dimensional space-time and the variations of them, and that's completely ill-defined. So they come up with some really fancy tricks. If you want to consider quantum gravity, now you're varying metrics, meaning you're varying the manifold and the metrics on them, and the space of such things, wouldn't be even well defined. Nobody will be able to define a metric on such a thing, let alone do these integrals. But now what they do is that they set time to be imaginary. That takes that I to minus, and the S is typically a quadratic, and these integrals then make more sense. But just because it makes more sense doesn't mean that it's justified. So this Wick rotation is a complete baloney. And yet they get an answer that actually makes sense, at least in quantum field theory. And some people, clever people, have worked on trying to justify it. But there's a lot more work to be done. So anybody with good, analytic skills, there are deep, deep problems to work on. And that's what I'm going to propose. But here's the shocker. The universe has a finite limit as to how small we can measure things, or how short a time we can measure, or how temperature and energy. That means we can't measure things smaller than 10 to the minus 35 meters. And in fact, at the Large Hadron Collider, the best we can do right now is 10 to the 4 GeV. That's where we are. 10 to the 4, our most powerful accelerator, and we have 15 orders of magnitude to go. What the heck lives between now and Planck length? We don't know. Okay, so there's a lot more to discover. By the way, the reason we can't measure smaller, and I'll just take a minute to explain, is that you need this much energy to probe distance. The smaller you want to probe, the more energy you need to put in, and the more energy you put in, at this energy, at that size, you create a black hole. And what that happens is that part of the universe just closes itself out completely from our universe, and we will never understand it anyway. That's why there's a hard limit, and we can never escape that. Okay. All right. Now, what that means is maybe space-time itself is discrete. maybe the real line is a cover-up. Wow. That means everything you guys are doing is all baloney. It's just going out the garbage. But I don't believe that. Space-time can still be continuous, but we're faced with very difficult limitations that we don't know. Okay? And that leads us to the discrete path takes you to loop quantum gravity or non-commutative geometry. The continuous path leads us to strings and other sort of superstrings. So let's get back to a more classical world, which we enjoy more anyway. This is an eye chart, but what I want to tell you is that that's the sort of mathematical formulation of Yang-Mills field theory. But what it is a vector bundle over space-time with a connection and a curvature. The Yang-Mills functional is the L2 norm of the curvature. And what you want is that at least to be finite, but in fact, if you want it to minimize it so that in the integral, path integral, it'll make the most contribution, then you may want to look at self-dual Yang-Mills or anti-self-dual. Those are known to minimize the Yang-Mills functional. And Donaldson, Friedman, and others went to town with it. And I'll tell you a little bit about it. So Friedman was just working in topology, but Donaldson was actually using the moduli space of self-dual or anti-self-dual Yang-Mills fields and trying to understand that as a tool, the moduli space as a tool to understand the base manifold. Now, that seems completely bizarre until you remember that, you had the problem of, can you hear the shape of a drum? Mainly solve the eigenvalue problem for the Laplace operator. That can tell you mostly about that. It's not an exact reconstruct. You can't exactly reconstruct the drum shape from it, but it's pretty close. Here, we're looking at a more complicated equation, the nonlinear Yang-Mills equations, and the behavior of their moduli can tell you something about the manifold. I won't go into it at all. This is an eye chart. You can read it. I'm happy to share these slides so you can read it at your convenience. Now let's get to the quantum theory. Now it's much more elaborate. And this is the Lagrangian of the so-called standard model of physics. It accounts for all the particles and fields that we know. 3 of the 4 fields, the 2 nuclear forces and electromagnetism, but does not account for gravity. It's not unified because it's a product group. It's explicitly product. And it can't account for gravity. There's more work to do. Okay. By the way, I just wanted to give you a chart comparing Riemannian geometry to connections on fiber bundles. There's a lot of analogy between them. By the way, you know the story that Einstein in 1955 on his deathbed was trying to figure out how to unify the forces, the 4 forces that he knew. And he couldn't do it with Riemannian geometry. A year after he died, the theory was well enough developed that physicists Yang and Mills took over this theory of connections on fiber bundles, and they went to town with it, and that's been successful. So Einstein didn't know this theory. Okay, I'm going to use another transform. You know about the Fourier transform, of course. There's something called a twistor transform that takes not even an even nonlinear PDE, like the Yang-Mills or the gravitation Einstein's equations, and turn it into an algebraic problem, but it's an algebraic geometric problem, not just pure algebra. Okay, so we're going to get into that just a little. Atiyah and company, basically Oxford and Moscow, got together to figure out how to classify all Yang-Mills, self-dual Yang-Mills solutions over the four-sphere S4 using a twistor space over S4, which turns out to be CP3, complex projective 3 space, and lifted the equations into that twistor space that becomes a pure algebraic geometry problem, and they could classify with just linear algebra, and it worked great. In the gravitational setting, it's even harder. Einstein's equations are extremely nonlinear, and the twistor space itself becomes much more complicated. It will not be CP3, but in the problem of a particular manifold called the K3 manifold, it's a 4-dimensional real manifold, 2-dimensional complex surface. Yao's proof of Calabi's conjecture proved that in particular this manifold had a Kähler-Einstein metric Ricci curvature equals 0. That was known, and physicists right away Hawking and company at Cambridge came up with an interesting idea what it had to look like. It had to look like basically a flat torus on the bulk of it, and then in 16 little modules, it had to look like a metric that two physicists had figured out, the Iguchi-Hansian metric. And that's bizarre, but I came along and looked at that and said, there's no way to match and patch these metrics because they're real analytic. You cannot patch these things, but there has to be a way, and there was a twistor way to do that. So I was able to take a twistor construction with K3 surface fibers and be able to show that, in fact, it has a Kähler-Einstein metric, and number two, it really does match the Hawking and Gibbons picture. So that's quite interesting. A couple of my papers from that era. Now let's get to something totally different still, the super frontier. By that, what I mean is supersymmetry. So in quantum field theory, we look at the trajectories of particles and the interactions, and they look like these Feynman diagrams. In string theory, your basic object is not a point, but a loop, and when they interact, they create surfaces, and there's no intersection point. Now, all the infinities that they keep encountering are because there is an intersection point where objects get infinitely close. Here, nothing can get infinitely close because they're smooth and they have finite dimension. And as a result, what Witten would say is that you had infinities here because you didn't respect smoothness. You didn't really respect the real line. You have these are not one-dimensional manifolds. Here, we respect the smoothness, and because of the two-dimensional object, these are really Riemann surfaces. In fact, all the interesting physics doesn't care about the conformal structure on this thing, so it really is complex analysis. And they're perfectly well understood, perfectly smooth, and there are no infinities. We don't have to use tricks. You got rid of tricks. Okay. So the thing about string theory, though, it needs 10 dimensions, but who the hell wants 10 dimensions? We live in a 4-dimensional space. How does that work? Well, but let's look at the achievements of string theory, namely that it unites quantum field theory and general relativity, can reproduce all elements of the standard model that we know and love, and shows very deep ties between math and physics. And but of course, those deep ties require something called supersymmetry, which has not been detected at the LHC yet. So supersymmetry, from this point of view, has to exist, and yet it's undetected. Okay. There's one further problem, though. There's so many solutions to string theory. Current estimate is 10 to the 700 some. We have a selection problem. Which one of these is our universe? That is another deep problem, and we have some ideas about that, but I won't be able to get into it. Anyway, those physicists who are really pretty smart can figure out that supersymmetry can tell you something about Morse theory, can tell you about the Atiyah-Segar index theorem, can tell you about mathematical problems in addition to doing physics. And for example, this particular paper by Juan Mandacena, which is the most cited paper in higher G physics, 25,000 citations, implies that we live in a holographic universe, that out there all the information is some far away surface at the boundary, and everything happening inside is determined by physics at the boundary. That's bizarre. Okay. They even can figure out this K3 metric that we couldn't figure out exactly. All I could do is only show asymptotic results. They can figure it out using string theory. So they have a tool in their hand which we don't know how to use, and they can figure out math problems that we don't know how to solve. Wow. Okay. Finally, they can reproduce the standard model. These are very new results, 2025. Now, I mentioned one branch was that if you believe in the discreteness, you can go towards non-commutative geometry. It's a way of reproducing ideas in geometry which are purely algebraic. Okay, that's bizarre. But Ed Witten has taken it seriously, and others have as well. And there are good models in string theory using non-commutative geometry. It's not the direction that I would like to see. I'd rather see something else, namely, if you really want to do superstring theory, you need not Riemann surfaces, but Riemann surfaces with additional nilpotent variables, called super Riemann surfaces. And you embed those in a complicated manifold, which would be a super manifold and not an ordinary manifold. Okay, I did a little work on it some years ago. Completely new horizons now. Where does this strange theory take us? You know some of these famous scientists, but there are also a rogues gallery of people who led us astray from the ordinary understanding of space-time. They've shown us that we live in a very bizarre world. These are the people who did it to you. Okay, I'll just show a couple of things. You know about the Hubble can find objects 13 billion light years away, which is almost at the Big Bang time frame. And these little red dots are the ones that are that old. You know about the cosmic microwave background from just 400,000 years ago. And it's sort of a baby picture universe because it tells you the distribution of matter and light from around the entire universe. I won't have anything new to say, but this slide you may not know. It's by Robert Digraph, who was a director of the IAS at one point. And he pointed out that the smallest scale we understand in 10 to the minus 35 meters, and the larger scale, about the size of the observable universe, life sits somewhere in the middle. And so things can happen at different scales that are completely unpredictable. Okay, finally, I'll just end with some open problems that I see. From my point of view, the deepest problems lie at the intersection of math and physics. And to me, there is no border. There's just a no man's land between these two fields. And that can allow us to understand new math and from their physicist tools that we're not familiar with. Okay, I think that's one thing I'll mention is that Witten was the first physicist to win a Fields Medal. I don't believe he'll be the last. All right, that's all I have. Thank you.